Well, hello and welcome to NPL. My name's Ann Curtis. I'm a senior research scientist in the time and frequency group here. And NPL is first and foremost a metrology institute, which means we deal with measurement science. And that really, at its most basic level, deals with the SI base units. And these measure things such as temperature, mass, and length. But I'm specifically going to talk to you today about the SI second, which has quite a convoluted definition, and I'll read it for you. The second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine levels of the ground state of the cesium-133 atom. It's the definition. And what I'd like to get across to you guys during this talk is, how did we get from the point where the sun was the thing that told time? And I think a lot of us still feel very intrinsically that the sun is what tells us what time it is. How did we get from that to this very specific definition of a second that has to do with atoms? So my talk will basically start with a historical overview of timekeeping, but really in terms of the drivers of timekeeping, what drives our needs for clocks, and what's the technology of measurement science over the years. And then at the end, what's our current state of the art? How do you make an atomic clock? And what do we actually need these types of clocks for today? Before I get deep into this, I'd like to go through a couple definitions, and I'll start with just showing you the difference between terms such as accuracy and precision. One way to describe this is in terms of you have an archer who is trying to hit the center of a bullseye. So here's our first archer. They're not very accurate, and they're certainly not very precise in trying to hit the center of this target. As we increase in accuracy, the archer becomes more accurate. These arrow points are now centered a lot closer to the point they were trying to hit, but they're spread out. They're not very precise. We can also increase in precision, and we can see the archer now has hit basically all the arrows in the same place. They're quite precise, but it's not very accurate. You see there's an offset now between where they were trying to hit and where they actually did hit. And of course, the perfect archer who's both accurate and precise. And this is related to measurement science in the sense that you can imagine in this system here where you're accurate but imprecise, two things could happen depending on what kind of shot this person is over time. You could get more and more arrows kind of centered around this bit here. And you can imagine that statistically you could start to believe, yeah, I really know where the center of that target is, even though my arrows are a bit spread out. But over time, instead of being centered around here, the whole kind of average could drift off to the side, and then you wouldn't have a very stable system. So that's the idea of stability over time. Then if you look down at this kind of inaccurate, precise here, I mean, clearly this archer knows what they're doing. They're always hitting the same spot. But there's some kind of offset, some systematic reason that they're not hitting the center every time. And if we could understand that offset and correct for it, or even just subtract it off, or in the case of this archer, just move the target over a couple of meters, then you would be in a position where you're both accurate and precise again. So these are the kind of terminology I'll be using during the talk. And when you go and tour the time and frequency section of NPL after the lecture, you'll hear these terms come up over and over again. So to summarize, accuracy is what helps you get to work on time. Stability or precision, it doesn't matter what time it is, but it matters that your clock is ticking at a regular, stable rate, for things such as measuring heartbeat, for example. And then there's a third thing that we like to talk about, which is called reproducibility, and that really has to do with how much do you trust your clock. If you're trying to compare your clock to other clocks, how does it hold up? So then I should really start with the basic question of what is a clock. So a clock is made up of an oscillator. An oscillator is something that's periodic. It means it repeats. So in terms of something you all are very familiar with, a clock with a pendulum, this periodic swing of the pendulum. It also includes electromagnetic radiation, which also oscillates in time. The second part of a clock is a counter, because you've got this radiation, but you don't know anything about it, or you have this pendulum moving, but there's no way to look at how it's moving over time. The counter then measures the oscillations. And in terms of the clock, That's the mechanism that takes each tick and tock and turns it into seconds, minutes, and hours and keeps track of time as it's going. The third thing that can be very useful for a clock is a reference. And the reference is really how you check that your clock is on time. And we'll talk more about that as we go on. So in terms of measuring time, if we're looking at the historical perspective, you really want to ask two questions. Why do people need to know what time it is? This need is what drives clock development. And how do those needs change over time? So you start with your kind of in historical times, local solar time, which is simply based on the motion of the sun across the sky. You have shadow clocks, even portable shadow clocks that can measure this, but the systematics, the things that cause your measurements not to be as accurate or precise as you'd like, is that the way the sun moves across the sky changes throughout the year. Of course, there are overcast days, and worse yet, there are 12 hours a day where you have no access to your clock. What evolved out of this were water clocks, and this is an innovation in timekeeping where for the first time you didn't have some motion of a body in space that gave you your time. And the way these work is you're either measuring how long it takes for one cistern to empty or how long it takes for one cistern to fill. These were invented essentially to measure time at night. You had night watches and getting the timings right for that. You had religious ceremonies. You could use them indoors to measure how long you were debating in court. You had portable versions for measuring pulse rate and things like that. But the systematics are you're not going to have a constant flow rate, either into or out of one of these cisterns. And there are things that affect the flow rate as well, though you can calibrate these kind of things with a sundial. And that's what they did in terms of innovations where you started putting markers to measure time so you could see what time it was by the level of your water, or even more ingenious devices where as the water fills up, it pushes a lever which turns a gear, which then indicates the time on the face of a clock. And these are starting to look like real clocks now, as we know them. And then, of course, you could have a really elaborate example which played music and created motion and could even show you the movement of celestial bodies over time through the mechanical motion of this water clock. But what we really needed in terms of increasing the accuracy and stability of these clocks was something that would oscillate, that would have a periodicity that was much more constant than this flow rate of these water clocks. And that came about with the invention of pendulum clocks. And why this is really so powerful has to do with the intrinsic systematics of the system. If you look at what defines the period of a pendulum, that is the time it takes for a pendulum from one point to swing and come back to that same point, is simply a square root of the length of that pendulum, and that is the length from the point of which it's swinging to its center of mass, and the acceleration due to gravity where that clock is. And those are the only two things, as long as your oscillation amplitude is small, so small little oscillations like in a clock. Those are the only things that affect the period, the timing of this period. What is not in this equation is mass. It doesn't matter how heavy your pendulum is. And the other thing that's not in there is the amplitude of the swing. So if that changes a little, it actually doesn't affect the oscillation period of your clock. So the systematics are now much more subtle. It has to do with small changes in the length of the pendulum with temperature or friction due to the air that's involved near your pendulum swinging. And people found ways around these to compensate for these changes. And then you could have pendulum clocks that had errors of less than 10 seconds in a day, which means that the deviation from the steady, calculable oscillation frequency would only be 10 seconds lost or gained in one day. What was driving the need for these more and more accurate clocks? Why couldn't we have just stayed with water clocks? Well, one thing that was really driving things both economically and otherwise was navigation in the 17th century. And around that time you had all these observatories that were opened in these different maritime nations because they wanted to know where they were when they were traveling in the ocean. And this all has to do with the longitude problem, which I'm sure many of you are quite aware of, but I'll explain it in some detail here. So your latitude, which is your measurement of where you are north and south, is actually fairly simple to measure. It has to do with the sun's angle at noon. So you can figure out where you are north to south fairly easily. And in fact, you can measure what time it is where you are by the sun quite easily as well. But what you can't do easily is find your horizontal or longitudinal position on the globe, unless you know the time at some reference point. And so what you can think is, if you can draw a circle around the Earth here, you can split that circle up into 360 degrees. And if we have a 24-hour day, that means that as you travel 15 degrees, that's the equivalent of a time change of 1 hour. Now, let's say you started in Greenwich and you synchronized the clock in your hand to some Greenwich clock. And then you traveled some distance from Greenwich and you wanted to know where you are because you're in the middle of the ocean now. Well, all you need to do is measure your local time, compare it to the time on your clock, and let's say you saw exactly a 3-hour time difference, you would know you had traveled precisely 45 degrees from Greenwich, and you would know your position very accurately. Clocks at this time, these pendulum clocks, could make these measurements at the level necessary to know where you were. But unfortunately, pendulum clocks were not really good on a boat. And this led to this Longitude Act of 1714, where the government put together a 20,000-pound prize if you could measure the longitudinal position to half a degree. And the error on that kind of error is about 35 miles at the equator, and equivalent to a clock that can keep time to 3 seconds per day. And to give you an idea of how important this was, both economically and militarily to the government at the time, 20,000 pounds prize money then would be the equivalent of about 1.5 million pounds prize money now. So they were taking this quite seriously, and took John Harrison a long time to get the money, but he did demonstrate a clock. And you can go, if you go to Greenwich, they have the whole series of clocks he worked on towards this work, and a whole history of this longitudinal prize laid out quite well. I highly recommend it. But he created a seagoing clock that is actually not that large, that was accurate to about 0.2 seconds in one day. But what that meant in reality was, over a 7-week trip he took to prove that his clock was good, the error in their position was only about 30 kilometers. And so this meant for the first time you could safely sail across the oceans, and the kind of navigational needs were being met by the clocks of the time. But of course, as you try to get better and better timing and know your position better and better, you run into the subtleties of the system you're using. Noon, I'm saying it's quite easy to know what time it is where you are, but noon is not the same as the sun being directly overhead, it turns out. And this varies by about plus or minus 15 minutes over the course of a year. So the international community decided to use instead a mean annual average of this non-uniform motion of the real sun. And it was at that time that the second was then defined as some fraction of the mean solar day. And this Greenwich Mean Time was established as a global standard in 1884. The problem with this, although it was good enough at the time, is any definition of time that's based on the rotation of the Earth is going to run into trouble, because the rotation of the Earth is not constant. So why does the Earth's rotation have some variation? Well, it really has to do with conservation of angular momentum at its heart. But the idea is that the mass of the Earth, it doesn't all just stay in one place. And you also have the Moon and Earth mass system as well. And as you change the mass distribution around, it changes how fast the Earth rotates. And these can be kind of large changes or small changes, fast or slow. People have known that there's a difference between Earth rotational time and this mean solar day time, and have been measuring it since kind of the 1650s. And you can see that the differences can be on the order of tens of seconds over these centuries it's been measured. But it's not just a long-term deviation on a daily basis or a yearly basis. These are year indicators here, basically. You can see that the speed of rotation differs from this Earth's rotational time on the order of milliseconds now. So if milliseconds are kind of the timing that you need, you have a problem if you're defining time in terms of this rotation. So what this is really telling us is, the sun moving around the Earth is not a good enough reference. The Earth is not a good enough reference. We really need to reference our clocks to something more stable. And that's where the introduction of atomic time comes from. This idea that we can reference our timekeeping to atoms. And the first cesium atomic clocks were produced at NPL in the 50s, and they were accurate to a part in 10 to the 10th. Now, to compare that to the clocks we've been talking about, that's as if you ran your cesium clock for 300 years, and it was only changed in time had an error of about 1 second. And that's comparing this 0.2 seconds per day of this kind of best navigational clock before that. Other labs quickly reproduced this and showed that yes, this clock does keep this kind of time, and because of this reproducibility, the cesium clock was adopted as the basis for this international definition of time, which I read to you at the beginning. This GMT then was replaced by an international time reference, UTC, which is still used today, which is maintained by an ensemble of atomic clocks to which our cesium fountains give data every month. And just as a note, leap seconds were introduced at this time because although we're now keeping time with atoms, which don't care how the Earth is rotating, people still live on the Earth and it rotates, and we still want the sun to be approximately at noon when it's noon and not drift away from that over time. And so that's why the leap seconds are added in. It just keeps UTC and Earth's rotational time constant to within a second. So in terms of microwave standards today, because this 9 billion oscillations per second of the cesium clock definition is a microwave transition, these kind of clocks, which you can see if you go visit down in our labs, they have an accuracy of about a part in 10 to the 15, which in the terms I've been talking about is a clock who would only lose or gain a second every 3 billion years. So the real question is, how does having a clock referenced to atoms give us so much better accuracy than these clocks that are based on pendulums and internal workings? And that really has to do with the fact that these atomic clocks, the oscillator in the clock itself is electromagnetic radiation that's then referenced to an atomic sample. And I'll go through that because this is quite important to understanding how atomic clocks work. So if you have kind of an electromagnetic spectrum and energy is increasing on this axis, you have the kind of low energy radio waves, the visible spectrum from red to blue, and then kind of UV and X-ray as the energy increases. And you can also talk about frequency. The frequency of the oscillations increases as well. Frequency and energy are proportional, so you can talk about them in the same way. According to quantum mechanics, atoms and atomic systems have quantized energy levels. And very basically, that means that when you have your atom with an arrangement of electrons, there's kind of a low energy state where these electrons want to be in. And you can shine any kind of energy you want on the system, and nothing will happen until you shine just the precisely correct radiation on your atom to excite those electrons into a new configurational state. So you can shine whatever you want on this atom, but it won't become excited until you get the frequency exactly right. And it's the precision at which you have to get this frequency right that makes these clocks so stable. So the atomic clock is basically made up of an oscillator that produces the radiation. So if it's a microwave clock, that's a microwave cavity producing microwaves. If it's an optical clock, that means it's in the visible, and that's laser technology that produces the radiation. You have a counter of some sort that measures the radiation. And then here's your atomic reference. And the reason, again, this is so important to the atomic clock is this oscillator is not going to do anything to this atomic reference until you get the radiation frequency exactly right, in which case your atomic reference will produce a signal that you can use to tell the oscillator it's gotten the frequency right. And this is the basics for the atomic clocks. And the reason that atomic clocks are, again, so powerful on top of that is atoms of the same element and the same isotope, that's the 133 bit of the cesium, are identical. And that means if you make your clock somewhere else, the atoms are going to behave exactly the same way. So all of a sudden, these clocks are extremely reproducible, unlike any kind of pocket watch or a pendulum clock you can imagine. So what's driving this modern day clock development to, just a few seconds in a billion years? Well, navigation is still driving it, except now on much larger time scales and much larger length scales. You have synchronization, where you have large arrays of things that need fine timing control. And this idea of radio telescopes is just fascinating, and I highly recommend looking into it. So you need the clock on each of these to know the time and the synchronization between all the other clocks. And again, just the kind of economic and public needs are still driving this forward. So to finish up, I wanted to give one concrete example so you really, really understand how the accuracy of these clocks directly feeds in to these modern day drivers. And I thought I'd do that by explaining how global navigation satellite systems work, because although everyone, I bet, in this room has a phone that can tell you where you are, I don't think many people are aware exactly how that works and how vitally important the clock development that we're doing here and at other national metrology labs feeds into this kind of thing. So first I'll just explain how does it work, and then hopefully by the end of it you'll understand why clocks are so important. So I'll do that with just a basic example of time of arrival ranging. And I'll call this the foghorn example, because the idea is the sound of a foghorn is going to allow us to know where we are, to find our location. So let's imagine we're a boat, and we're about to sail off, and before we do, we synchronize clocks with a whole bunch of other boats. So we've all synchronized, so at 5 o'clock, it's 5 o'clock on all the boats. The reason this works is we know the speed of sound is about 335 meters per second. Now, velocity is simply how far something travels over a certain amount of time. In this case, meters per second is how we've defined this. But you can change that equation around, and you can, from knowing the velocity and the transit time of a signal, you can know the distance that that signal has traveled. And that is basically the whole idea here. So if we set off a foghorn at a certain time, say 5 o'clock, and I, on my boat, measure that foghorn coming in a couple seconds later, you can then, from that information of knowing the velocity and the time it took between when the signal was sent and when you received it, you can now know your distance from that signal. Now, of course, you could be anywhere along the circumference of the circle this played out. So then you just need a second boat who also has a foghorn. It'll circumscribe another circle. So now there's 2 points you could be at where those 2 circles intersect. So with a third boat, you then precisely know where you're located. So what do clocks have to do with this in terms of accuracy and precision? Well, let's imagine there was a slight timing offset. After you synchronized your clocks, one of the clocks has moved a bit. Let's say it's moved by about a second. So there's a second offset between the 2 clocks, but of course you don't know this because you aren't next to each other to check. The speed of sound is 335 meters per second, so this small error in your location is going to be equal to the speed of sound times whatever this small offset is. And so that leads you to a 335 meter error. And of course, that gets added to the errors produced by the other timing errors on these other boats, and instead of one very precise point that you know you're at, there's now this large area where you could be located. And so the moral of this story is that timing errors in your clocks, reduce the accuracy of your position measurement. Satellite navigation works in precisely the same way. You have a receiver on the Earth, a satellite in the sky. They have clocks that are synchronized at some level. There's some distance delta x you would like to measure. The same equations apply, but now instead of the speed of sound, you're dealing with the speed of electromagnetic radiation, which is much higher. And this, of course, leads to, and if you want, say, sub-meter accuracy, you're going to need nanosecond timing in your clocks. Now, the clocks we have aboard these satellites are microwave clocks, and they can very easily get this kind of timing and get this kind of precision in placement. So what's next? Well, we keep making better and better clocks because there seem to be more and more applications for them as we do. The optical clocks we're developing here and at other places in the world, they are clocks that would not lose 1 second over the lifetime of the universe. And there are actually reasons why that's necessary, which I very briefly will show you. And at this level, Earth-based clocks start to run into problems, which I don't have time to go into, but please feel free to ask me afterwards. And so your solution really is to put your optical clocks in space. And that gets around all these issues. And then you suddenly can access better navigation, tests of fundamental physics. There's geoscience you can do in terms of motion of tectonic plates. In terms of synchronization, you can now have even larger arrays of things even in space where you're trying to do, say, gravity wave detection, radio astronomy in space, deep space communications where the distances are, again, now astronomical. And what has history shown us? It's said that in terms of clock development, it's always kind of economic drive that pushes things forward But really, the better we make the clock, the more things we can do with it. So thank you for your time. And if you have questions, I'll be in the cafeteria just down the way, and I'll be happy to answer them.